The proposed method for integrity verification of measured transformer currents is suitable for the modular development of hardware-in-the-loop digital twins, HIL DTs. It utilizes the Adaptive Extended Kalman Filter to estimate the parameters of transformer currents, which can be non-sinusoidal during transients such as transformer energization. The method is evaluated using EMTP-RV for simulating transformers and Matlab for executing the proposed method. The simulation results demonstrate that the method is able to accurately estimate and closely track the current measurements. The proposed method employs a recursive method for integrity verification of measured transformer currents, which is suitable for the modular development of HIL DTs. The differential equations, DE, describing transformer transients are relatively complex, requiring the use of numerical DE solvers with small time steps. This implies that replicating transformers with HIL DTs requires a continuous flow of accurate measurement samples with a high sampling rate. The proposed method utilizes the Adaptive Extended Kalman Filter to estimate the parameters of transformer currents, which can be non-sinusoidal during transients such as transformer energization. Then, after evaluating the validity of estimations, the proposed method utilizes the estimated parameters to reconstruct noiseless measurements with desirable sampling rates. The performance of the proposed method is evaluated using EMTP-RV for simulating transformers and Matlab for executing the proposed method. The simulation results demonstrate that the method is able to accurately estimate and closely track the current measurements. The advantages of the proposed method are as follows. 1. It is able to estimate the parameters of measured currents even when the transformer is heavily saturated. 2. It is computationally effective owing to its recursive mathematical formulation, which is suitable for implementation in industrial computers. 3. The proposed method adaptively modifies itself with respect to measurement noises, which increases its accuracy and trackability. The paper presents a method for estimating the parameters of a transformer current using an Adaptive Extended Kalman Filter, AEKF, and a noise parameter estimator module. The current parameter estimator is the first module, which processes a measured sample of transformer current to estimate the magnetization. The paper presents a novel approach to estimating the magnetic flux linkage in a transformer using the Augmented Extended Kalman Filter, AEKF, method. This method is designed to handle the nonlinearity of the transformer's magnetic circuit and the uncertainty in the measurements. The AEKF method estimates the magnetic flux linkage by combining the measurement of the transformer's current and voltage with the mathematical model of the transformer. The paper first describes the mathematical model of the transformer, which includes the equations for the magnetic flux linkage, the voltage and current relationships, and the magnetic circuit's nonlinearity. The AEKF method is then introduced as a means to estimate the magnetic flux linkage by recursively updating the state vector and error covariance matrix. The paper also discusses the normalization of residuals, which is crucial for evaluating the validity of the estimation. A threshold is calculated based on the probability of false alarms, and if the normalized residual exceeds this threshold, the estimation is considered invalid. The AEKF method is applied to a single-phase transformer and a 3-limb, core-type, 3-phase transformer. The simulation results show that the proposed method can accurately estimate the magnetic flux linkage even in the presence of noise and nonlinearity. The estimated currents closely match the measured currents, and the errors in estimation are negligible. The paper concludes that the AEKF method is an effective tool for estimating the magnetic flux linkage in transformers, providing a means to monitor and control transformer operation in real time. This approach can be particularly useful for applications requiring high accuracy and reliability, such as in power systems and electrical engineering. The paper discusses a recursive method for developing measurement integrity verification suitable for transformer currents. It highlights the importance of ensuring the quality of current measurements in hardware in the loop, HIL, digital twins, DTs, replicating transformers. The proposed method utilizes the Adaptive Extended Kalman Filter, AEKF, to estimate parameters of measured currents and evaluates these estimations using hypothesis tests. Valid estimations are then used in the reconstruction of measurements, significantly improving the performance of DTs. The paper presents several tests to validate the proposed method, including an inrush test and an underload switching test. In the inrush test, the mean squared errors, MSEs, corresponding to switching angles near 45 degrees are slightly smaller, indicating less error in estimations when the switching angle is close to 45 degrees. The estimated magnetization component becomes valid considerably faster than the sinusoidal component regardless of the switching angle. In the underload switching test, the differences in voltage magnitudes and phases cause a flow of reactive and active powers through the transformer. The proposed method is capable of tracking the currents, and it is clear that the LV current becomes zero after disconnection from the LV side. However, the HV side stays connected and draws the magnetization current. The normalized residuals show abrupt changes in both LV and HV currents due to the LV side switching. The paper also discusses the performance of the proposed method in a core type, 3-limb, 15 kVA, 60 Hz, 208 Y, 240 delta distribution transformer. Although the core becomes highly saturated, the proposed method is able to estimate the currents since the normalized residuals mostly consist of noises after a short while. The estimated sinusoidal and magnetization components are successfully estimated, and the overall effect of the proposed method in improving the performance of DTs is discussed with reference to a figure showing the measured no-load current of phase A without additive noises, with additive noises, and the reconstructed measurement at a high sampling rate. The proposed method for estimating transformer current measurements is evaluated using EMTP-RV and Matlab. The results demonstrate the method's capability to satisfactorily estimate current measurement parameters and track changes in transformer currents, even in intense saturation. The magnetization current of each phase is divided into two parts, induced by limb and yoke inductors. The linear combinations of nonlinear currents passing through limb and yoke inductors result in functions of the same type as their constituent currents. In hypothesis testing, the null hypothesis states that the normalized residual is caused by noise, while the alternative hypothesis states that it is not caused by noise. A false alarm is released when the residual is induced by noise but is found to be caused by other events. The proposed method is compared to existing digital twin technologies and their applications in power systems, transportation systems, and smart cities. The development of digital twins for power transformers, distribution power transformers, and electric power drive systems is discussed. The paper also reviews existing research on digital twin modeling for photovoltaic panels, power transformer remaining life prediction, and fault diagnosis in PEM fuel cell systems. The application of digital twins in power systems, including microgrid security, distribution network reliability forecast, and transformer fault diagnosis, is discussed. Furthermore, the paper presents a comprehensive review of existing research on hypothesis testing, digital twin development, and power system state estimation. The references provided cover a wide range of topics, including digital twin technology, power system monitoring, and fault diagnosis.